All right. Well, good morning, everyone. As Kurt said, my name is Jason Haegele. I'm the North American Agronomy Lead for ICL. And I think for most people, ICL is probably an unfamiliar company, but like Netafim, ICL is a company based in Israel. It's been around for 100 years now, or a little over 100 years, and it really goes back to the Dead Sea. And the Dead Sea is unique in that it's a very salty water, actually several times saltier than the ocean. So there's a lot of potassium in the Dead Sea, magnesium and bromine. And that's how ICL got started, was extracting those elements, those nutrients from the Dead Sea to make fertilizers, to make industrial products like flame retardants, and create water-soluble fertilizers. And so that's really what I'm going to focus on this morning, is talking about water-soluble fertilizers like ICL's PEC acid product. And then talk about how water-soluble fertilizers like PEC acid, as well as some foliar options, can be used for corn and soybean nutrient management. So first I want to talk a little bit about water quality and really what are the issues as it relates to fertilizer source, water quality, pH, and how those things interact. Often we think about incompatible fertilizers, and this happens whether you're putting something as a foliar application or a side dress application or fertigation. We have to think about those fertilizer sources and whether they mix well or don't mix well. But we can also extend that to the interaction between fertilizer sources and water quality. And as we think about high pH water, high calcium water, hard water, all of those things influence the effectiveness, the efficacy of fertilizers, particularly as we think about phosphorus fertilizers that we put through a drip irrigation system. Hard water, specifically think about dissolved calcium, magnesium, cations, those positively charged nutrients. Those are typically what are going to cause us issues with that phosphorus compatibility. Calcium phosphate forms, it becomes insoluble and starts to block a drip line. As we see here. So, some different examples of different irrigation systems where we get that scaling, that buildup on the emitters, which can block an emitter completely, or at least the situations where maybe we have that variability in water coming out of each emitter. In this example here, where we've got just a very small amount of water coming out of one emitter, and then more water coming out of other emitters in that drip line. And as we look at this picture down here at the bottom, this is an example of what that fertilizer incompatibility can look like, particularly in a situation where we have hard water or a lot of calcium in the water, or in specialty crop markets across the U.S. where they're intentionally fertigating things like calcium nitrate, which often can't be combined with phosphorus unless we have some kind of acidification being used to ensure that compatibility. This vial here on the right, this flask, is starting to precipitate, so that would be an indication that we've got calcium phosphate forming, and over time that'll settle out to the bottom of the jar. Or if you think about your irrigation system, it would settle out in the dripper line or block the emitters. So specifically thinking about phosphorus, many times you might have seen a chart like this as people talk about soil fertility and the importance maybe of liming, or just in general the interaction of soil pH and phosphorus availability, or the interaction of soil pH and nutrient availability in general. And so the idea here is that depending on the soil pH, whether it's acidic or more alkaline, phosphorus can interact with other nutrients in the soil, like calcium at high pH, or with iron or aluminum at low pH. And so in parts of the U.S. where we apply lime to adjust low pH to a higher pH, what we're trying to essentially do is to bring that pH to the sweet spot where phosphorus has its maximum availability. But in a fertigation system where we're working with hard water or high pH water, really what we're trying to do is to go the opposite direction. We're trying to make the water more acidic, again, to try to reach that acidic zone, or that sweet zone of maximum compatibility between phosphorus and then those cations like phosphorus or magnesium that might be present in the water. If you look over here on the right side, I've got different fertilizer sources listed and the pH of the solution that they create. So if you think about common things like urea, very high pH, urea ammonium nitrate, UAN, that would have a neutral or high pH as well. Ammonium sulfate is going to be a little bit on the acidic side. But as we go down the list here, kind of in line with what Kurt was talking about of identifying, fertilizer sources that also acidify, there are options like ICL's PEC acid product, which has a 0, 60, 20 analysis, so 60% phosphorus, 20% potassium. That in solution has a pH between 1 and 2, so very acidic. And then a similar product called Agrilution pH Low that contains all 3 nutrients, nitrogen, phosphorus, and potassium, but that phosphorus is being derived from PEC acid, so it also has lower pH compared to many fertilizer sources that could and potentially be fertigated through an irrigation system. So we talk about bicarbonates, but really what are bicarbonates? They come from the ground, they come from groundwater, and the idea is that at some place deep beneath our feet there are there's limestone, so we have limestone aquifers, and over time that limestone is dissolving, releasing carbon or CO2 into the water. But the idea is that at that deep depth water is under pressure, and that carbon is in the form of a gas, CO2. But as we start to pump it to the surface, we lose pressure, and those bicarbonates start to form. And bicarbonate is an HCO3 with a negative charge. And so, in principle, what happens is that HCO3 is like the resistance. So if you're trying to acidify the water, initially the acid, the H plus that we're adding, reacts with this, and we have to add more and more acid to overcome those bicarbonates, depending on how much resistance or buffering capacity we have in the water source, depending on the bicarbonate concentration. Also, if you look at a water quality analysis, there might be carbonates listed on there as well, and really, the balance between bicarbonates and carbonates, depends on the pH. Won't go into this in a lot of detail, but if we look at a water quality report, and Cortland and the NutriDrip team can walk through this in greater detail, depending on your specific water source. But we look at things like total alkalinity, which is the combined measure of those bicarbonates and carbonates, which collectively are that resistance to acidification or resistance to change. Higher level or a higher alkalinity indicates more acid is going to be needed to bring the pH of the water from a high pH down to the optimal zone of say 6 to ensure that we have good compatibility between things like phosphorus and the nutrients that we're trying, other nutrients that are present in the water. So here's one example. This is a 8.6 pH water source, and if we look at the total alkalinity on the water quality report, it's reported at 261 parts per million. And so you get numbers like that, and the question becomes, is that good? Is that bad? What do you actually do with that? Depending on the state, they'll have different recommendations. But if we look at this example for alkalinity hazard levels for field crops like corn, soybeans, etc., that 261 parts per million of total alkalinity would fall in the severe category. Also, if we look at bicarbonates, so again, 306 parts per million on this report, and down on this chart, looking at bicarbonate hazard levels, again, that would indicate that this water source is high in bicarbonates and potentially going to be detrimental to the crop, or at least a challenge to the nutrients that we're trying to apply through the irrigation system. Okay, so if you have high pH water, high alkalinity water, what can you do about it? Or what do you do about it? And in principle, the approach is to acidify the water using historically acids like phosphoric acid, sulfuric acid, nitric acid. Kurt was talking about urea sulfuric acid, that reacted product. Those are all tools that can be used to acidify the water and address those bicarbonates that are present in the water. This table's comparing different acid types: phosphoric, sulfuric at a couple of different concentrations, and nitric, and looking at their neutralizing power. So the first thing that'll jump out on this is that a high concentration or high strength sulfuric acid has a high level neutralizing power, suggesting that it's a strong acid. It doesn't take much to acidify the water. But what's the challenge with that, Kurt? Is sulfuric acid fun to work with? Yeah, it's dangerous because it has a lot of neutralizing power. In other words, it can neutralize the water, but it can also neutralize you if not used used safely. So pec acid, and we'll talk more about what pec acid is, but the question is, where does pec acid fall into this crowd? And just based on some calculations that I've done, 1.23 ounces of the dry product, or if we've already put it into solution and have a concentrated liquid product, 2 fluid ounces, both of those per 100 gallons of water will neutralize 50 parts per million of alkalinity, which roughly falls in line with lower concentration of battery grade sulfuric acid, nitric acid, or phosphoric acid. So point is a pec acid as an acidifier is a great option to acidify the water, but it also has that additional benefit of supplying crop nutrients, phosphorus and potassium. So pec acid, if you haven't seen it, it's a dry product. So it's a dry, crystalline fertilizer. It's white in color, and this is a product produced in Israel, near the Dead Sea. So it's combining potassium, extracted or harvested from the Dead Sea, as well as phosphorus that's mined in the Negev desert of southern Israel. It has an analysis of 0, 60, 20. So in terms of water-soluble fertilizer options that are out there, comparing to things like monopotassium phosphate, which is 0, 52, 34, or MAP, monoammonium phosphate, which is 12, 61, 0 in its water-soluble form, pec acid is a very concentrated nutrient source supplying both phosphorus and potassium. One of the really strong points of pec acid, thinking about it as an acid, is that it's safer to handle. If you get some dry product on your hands, if they're a little bit sweaty, then your hands will start to tingle a little bit, but you're not going to get a burn like you would if you were working with concentrated sulfuric acid or any of those other products that I listed. Solubilizes quickly, particularly if we have warmer water or agitation, and it has a high level of solubility, around 5.5 to 6 pounds per gallon of solution, compared to some of the other phosphorus sources, which can be around 2 pounds per gallon in the case of something like monopotassium phosphate, MKP. The phosphorus in pec acid is in the orthophosphate form, so we've heard of polyphosphate, things like 1034O, or things like 9189, which is tends to be higher in orthophosphate. But all of the phosphorus or phosphate in pec acid is in the orthophosphate form, 100% of it. The potassium that is supplied from pec acid is in a chloride-free form, so it's has greater crop safety compared to something like potassium chloride, or also known as potash. It's compatible with calcium and magnesium fertilizers. Those are typically not things that you might consider fertigating for corn and soybeans, but those become more important, especially crop markets. And we certainly can have high levels of calcium and magnesium already present in the irrigation water that have the potential to interact with phosphorus in a negative way, unless we have this low pH or acidification coming from pec acid. One of the watch outs with pec acid, and this is really true of all acids, is that there can be some negative interactions with thiosulfates, so things like ATS, ammonium thiosulfate, or KTS, potassium thiosulfate, and that really just comes down to the chemistry of the thiosulfate molecule. If we get below a pH of 6, that can start to essentially break down and cause some compatibility issues. I already hit on this, but relative to other water-soluble phosphorus sources, pec acid is very soluble. It's probably the most soluble phosphorus source that we can use for fertigation. These numbers are in grams per liter, but thinking about kind of pounds per gallon, pec acid is leading the pack at around 5.5, 6 pounds per gallon. MKP is on the other end of the scale at around 1.9 or 2 pounds per gallon. MAP being a little bit more than that, and then stepping up to DAP, and then finally pec acid. And the last comment I'll make on pec acid is that this is not a new product. It's actually been around throughout the world for about 20 years now. Having started in Israel, having gotten its start in the irrigated cropping systems of the desert, came to the United States and really got established in California and Arizona, and those heavily irrigated, drip irrigated cropping systems, And now with NutriDrip's partnership and collaboration, we're exploring its use in the Midwest and corn and soybean markets as well. So over time, our customers have learned about using pec acid, but we've also done some trials and lab studies as well. This is one example from Arizona, looking at a couple of different heavy clay soil types from Arizona. These top two tables are one soil type, and then the bottom two tables are a different soil type. Essentially what was done in this trial was that we compared the untreated soil to different rates of pec acid applied on the surface, mimicking surface laid drip tape. So 10, 15, and 20 pounds of pec acid per acre. So if you look at any of these tables, in this column here specifically, you see the drop in pH that's occurring in the soil from the application of pec acid. You see the increase in potassium from the application of pec acid. You see the increase in phosphorus from the application of pec acid. Both of those make sense because pec acid contains phosphorus and potassium. But the other thing, if you study this closely, is that we're getting an increase in availability of magnesium in this specific example. And we've also measured or documented this for micronutrients as well. Thinking about micronutrients specifically in the soil, they become more plant available as the pH drops. So without acidification, micronutrients might be more limiting in this situation with these higher pH soils. But by applying an acid and bringing the pH of the soil down, we're liberating more micronutrients and other nutrients like magnesium and making them more plant available. All right, so let's dive into corn specifically, and I want to highlight why I believe fertigation in general is important for corn and soybeans, and think about when we might start to apply nutrients like phosphorus and potassium that can be supplied through products like pec acid for both crops, corn and soybeans. So where we can start is thinking about how much nutrition does a corn crop need, and depending on where you're at and your management practices and historical practices, yield level, these numbers can fluctuate somewhat. But the idea here is that, with macronutrients specifically, nitrogen, phosphorus, potassium, magnesium, and sulfur, a high-yielding corn crop or a high-yielding soybean crop requires a lot of nutrients. And for some of these nutrients, a lot of the nutrition ends up not on the leaves, not in the stalk, not in the residue, but actually ends up in the grain. And so when you harvest that grain and take it to the elevator, feed it, whatever the case may be, those nutrients are leaving the field, and we refer to that as crop removal. And so specifically, a nutrient like phosphorus, for a 230 bushel per acre corn crop, it requires about 100 pounds of phosphorus per acre in that corn plant at harvest, at maturity. And so that's considering the phosphorus in the grain, the phosphorus in the stalk, and the phosphorus in the leaf, all of the above ground part of the plant. Of that 100 pounds of phosphorus per acre in the corn plant, 80 pounds or 80% is removed with the grain. So a lot of that phosphorus is being moved into the grain, especially late in the growing season, and then ultimately leaves that field when it's harvested. It's one thing to understand the total nutrient uptake requirements for corn and soybeans, but even more important is to understand when the crop is demanding those nutrients or taking those nutrients up. That's the knowledge that helps us thinking about when we can fertigate the crop to its greatest effect, when we can make foliar applications to its greatest effect, side dress, however we're applying nutrients, we can optimize the timing of those applications by understanding when the crop needs those nutrients most. And so starting with nitrogen, this is kind of the typical curve. Across the bottom here we've got growing degree units following planting. We've got the growth stages, approximate growth stages starting in emergence and going all the way through grain fill. And what you see here is that early in the growing season, as you might suspect, the corn plant doesn't need a lot of nitrogen. It's a small plant, doesn't need to take up a lot. But as it starts to really start rapid growth or grand growth around V6, V8, going all the way up through those later vegetative stages, the demand for nitrogen is substantially more. And then the other thing that you'll notice here is that when we reach tasseling and silking, the requirement, the demand for nitrogen doesn't stop. It keeps going through the grain filling period. And so really the question becomes, how can we design our crop management practices, including fertigation, to supply some of these nutrients required in the latter part of the growing season. For phosphorus, there's actually about 50% of the phosphorus is taken up during grain fill. We think about phosphorus being important for early season growth, and that's why we think about starter fertilizers often. Making sure those little corn plants don't turn purple early in the growing season. Yes, phosphorus is important early in the growing season, but we need 50% of the phosphorus to be taken up in that corn plant, during grain fill. Often when roots are starting to decline, starting to shut down, and we need to find ways to pump more phosphorus into that plant to maximize its yield potential. And then finally, for potassium uptake, there's less potassium taken up during grain fill, but there's still a need for late season potassium. And if anyone's ever taken tissue tests later in the growing season, what is it that we often see, Kurt? We see lower tissue test levels, maybe even deficiencies of potassium lower or later in the growing season, and that's another opportunity where we can think about fertigation or other types of application approaches to make sure that we're getting that late season nutrition for late season plant health, and ultimately maximizing the yield productivity of that crop. All right. So kind of wrap all this up or summarize for corn. I was here probably about 6 weeks ago, and the ICL team sat down with the NutriDrip team, and we started to think about how we could incorporate some of the ICL products specifically for fertigation, but also think about more of a holistic crop management approach, including the fertigation, but also starter or 2x2 applications for growers who are set up to that type of approach, as well as strategically placed foliar applications. And so first focusing on the fertigation plan, we've got different options. We've got Agrilution pH Low. Again, that's a product that contains pec acid to provide that acidification, and specifically one that could be used as a product called Agrilution pH Low 6-31-31. So it's got 31% phosphorus and 31% potassium to have more of a balanced approach to supply both of those nutrients throughout the growing season. Or we can focus on pec acid 0-60-20 if we want to highlight phosphorus a little more as opposed to potassium. Depending on the product, or regardless of the product, we're thinking about 10 pounds per application, and around 4 applications or fertigation events throughout the growing season, starting in early to mid vegetative growth with a couple of applications, and then continuing through the reproductive stages or grain fill with 2 more applications. Another product that I'll explain about a little more later is an ICL product called Bio's Diamond, which is a humic product. And so I just put that out there to suggest or encourage everyone to think about a humic product, a folic product, depending, regardless of your favorite flavor of humic acid or fulvic acid. That's a great option to be including in these fertigation applications to synergize, to support the plant nutrition, support the plant nutrient uptake, and ultimately support yield potential. I have a specific example I'll talk about, but these products, Agrilution pH Low and pec acid, are not limited to fertigation applications. They are designed for all types of soil applications, so there are ways to include them in side dress applications, and there are also ways to use them for starter applications, whether that's a true in-furrow application or some type of 2x2 or off to the side of the row type of approach. So for Agrilution pH Low, I hit on this a couple of times, but there is an entire family of Agrilution pH Low products. With NutriDrip, we've really focused on a couple of different formulations within this Agrilution pH Low family. One of them being 11-45-11, so 11% nitrogen, 45% phosphorus, and 11% potassium, but it also contains 2% zinc. So this is a perfect kind of ratio balance for starter applications on corn, soybeans, and other crops as well. And it contains pec acid to provide that acidification which can be really key if you have high pH soils or soils with high level of bicarbonates as well in the soil profile. Bio's Diamond, you mentioned this briefly as well. This is a fulvic product, so 36% fulvic acid, some yeast extract as well, and molasses base. So we're getting a lot of sugars and carbons to not only support nutrient uptake and plant growth, but also to stimulate microbial activity as well. So I just want to briefly hit on the starter application as well, and reinforce the idea that pec acid and agrilution pH low can be a good fit for these types of applications as well, especially if we're considering or comparing against something like ammonium polyphosphate or 1034O. A lot of information on this slide, but really what I want to point out here is that we've got 2 years, same location, and the same types of consistent responses in both years. Treatment 1 is a control, so this received no starter fertilizer, and this was a true in-furrow application. Treatment 2 would be 1034O at 3 gallons per acre. So in both cases, you can see that there is a starter effect or a yield increase from applying 1034O, on average about 4 to 5 bushels per acre. And then if we look at treatments 4 and treatment 6, that's ICL's agrilution pH low product, 114511, applied at either 6 pounds of product per acre in this case, or 12 pounds of product per acre in this case. If you think about those 6 and 12 pound product rates, 45% phosphorus in the formulation, we're getting 2.7 pounds of phosphate in this treatment, 5.4 pounds of phosphate per acre in this treatment, and then 3 gallons per acre of 1034O is almost 12 pounds of phosphate per acre. So we're getting the same starter response, or in some cases, even a greater starter response from less phosphorus in agrilution pH low, and I believe that has to do with the acidification properties of agrilution pH low compared to something like 1034O that has a pH of around 6 or 6.5 compared to the pH of 4 that we have in agrilution pH low. For soybean, quickly go through the same kind of thing. This is a 60 bushel per acre soybean crop, so it's now by no means a record breaker. But if you look through this chart for nitrogen, phosphorus, potassium, magnesium, and sulfur, just like we did for corn, again, some of these nutrients are required in a very large amount, even for a 60 bushel per acre soybean crop. Specifically looking at potassium, 170 pounds per acre, and nitrogen, 245 pounds per acre. Like corn, for soybeans, there's a lot of phosphorus that's found in the grain and ultimately removes that field. 80% of the phosphorus taken up by the soybean plant is going to be found in the grain. For both phosphorus and potassium, the point that I want to get across here is that managing soybeans for high yield is a season-long game that you have to play. You can't give up after the fungicide pass. You can't give up after the post-herbicide pass. If you're looking at nutrient uptake, a soybean crop will continue to take up nutrition basically all the way through maturity and up until those leaves start to turn yellow and fall off the plant. If we look at phosphorus specifically, so we get to pod fill stages, we're only at about 50% of the phosphorus that's going to be taken up in that crop. There's still 50%, or about 20 pounds, 21 pounds in this specific example, that have to find their way into that crop in the last few weeks of the growing season as those pods are filling out and as we're trying to make those individual soybean seeds and pods as heavy as we can. And then similarly for potassium, if we were to go back and compare to corn, about 2/3 of the potassium, or maybe even a little more than that, is in the corn plant by tasseling, and there's still a little bit more that's taken up during grain fill. If we focus on soybeans, again, as we get to that kind of R5, growth stage or start of pod fill, only about 50% of the potassium has been taken up by that point, and there's more opportunities to get more potassium in the plant and maximize the yield potential of soybeans later in the growing season through fertigation through foliar applications and all of the crop management practices that we can use to support that yield potential. So similarly for soybean crop, we're focusing on the Agrilution pH low 631-31 product to get as much potassium to the plant as possible, or pec acid if we need more phosphorus or more acidification. And then the Bios Diamond, the humic or fulvic product, or any humic or fulvic product if you're choosing, is a great choice to apply in those fertigation applications. Primarily focusing on the latter half of the growing season, really around R3 or beginning pod formation, and then continuing into pod fill to maximize that late season nutrient uptake and yield potential. So I think with that, Kurt, I'm going to pause here or stop here, and if there are any questions, we'll answer questions or any comments, insights that you want to add or Tim wants to add. We have a little bit of discussion before we transition to the next speaker.
Any questions? I've got a couple. What about if I have low pH soil? What product would I want to use if my soil pH is low and I'm adding lime all the time? Would I want to go in with a 0-60-20, or what do you recommend if my soil pH is low?
And specifically, are you talking about a fertigation application?
Fertigation or a starter. Actually, let's talk about a starter first.
Okay. So I'll jump ahead to this slide that I didn't show. We had the same kind of starter trial that I showed for corn on soybeans in Wisconsin. And these were not high pH soils. These had a pH of around 6.5, so slightly on the acidic side. And these were the types of responses that we were getting. So even though Agrilution pH low is an acid-forming fertilizer, we were still having these nice yield benefits even compared to 1034-0 at a lower pH soil. And sometimes hard to explain kind of the rationale or how it works, but in general, where we've used these Agrilution pH low products or acid-forming water-soluble fertilizers, we're getting agronomically better results and better yields, even in soil types that are not high pH soils, they're not high carbonate soils, those types of things. So for me personally, just based on real-world trial data, I have no reservations about using Agrilution pH low, in particular because it's a little less acidic on these neutral or slightly acid soils. With something like pec acid, the 0-60-20 product that has the pH of 1 to 2 in solution, that's probably not something to use on a truly acid soil, especially at a high rate. And then kind of the second part of your question, thinking about the fertigation applications. Even though you have maybe a acidic soil or a soil with a pH less than 7, you still have to think about the water quality and the water pH, which can be higher than 7, much higher than 7, even on acid soils. And so there's still a fit for these acid-forming water-soluble fertilizers to treat the water, to improve the water for fertigation applications or uses.
Good. Is the amount of fertilizer we're going to put out with fertigation or a starter, is it going to impact soil pH long term? Like, is it enough product to actually impact it, speaking on 0-60-20, for example?
Mm-hmm. Yeah, that's a good question. So I showed this one slide from the trial in Arizona where we were having an impact on soil pH. We were bringing it down. But the thing that we haven't measured, we don't know, is how long that effect lasts. And in some cases you may be tilling the soil at some point, so you're going to disrupt that band and dissipate the lower pH. But I think certainly for the growing season in which the products are being applied, you're going to have a long-lasting effect on soil pH, right around the dripper line or right around the point of application. For example, in a starter application or some type of banded soil application, we're going to have that effect persist in the soil. But does it persist from year to year? That I don't think we understand yet.
Mick, can you back up to the slides on the alkalinity and bicarbonate? I want to touch just a little bit on that. While he's doing that, one of the things I'm sure everybody's thinking about cost, like how do these products line up cost-wise? So if you're willing to do the solubilizing yourself, you're going to be roughly $3 a gallon. Okay, so it's a little bit more expensive than 1034-0, but it's about half the price of, say, a Conklin or a Nature's, some of those pre-solubilized stuff. So as I look at it, the benefit that you're getting, if you're willing to do a little bit of work and solubilize it, which is not that hard, it melts about as easy as AMS, I would say. So ammonium sulfate that you put in your sprayer, it's going to be similar to that. You can use an inductor, put it in the tank, just have some agitation going. It's fairly easy to solubilize. But the cost effectiveness, from what I've done the math on, looks reasonable. Go to the slide where you had the chart of the different tables of bicarbonate, and there you go, right there. So alkalinity hazard levels, high and severe is anything over 200. Does anybody know what their alkalinity is in this part of the country? Most of us are 300 to 600. Okay, we're off the chart, like way off the chart. And especially in Nebraska, Kansas, we were down in Lamar, Missouri yesterday. They have some that are around 100 to 150. They have some good water. But northeast Kansas, southeast Nebraska, we're off the chart. Eastern central Nebraska, way off the chart. Same thing on bicarbonate. Go to the bicarbonate table. So they're calling severe anything greater than 244. Our bicarbonate level right around here is about 350. Darren, those wells over there are around 600. So you're like way over on the chart. So just know that like there is an issue here, and we haven't been addressing it. Yeah, it's a good question. So if you send it to a lab, surface water comes back. So, well, first of all, let's go to catching the rainwater. So catch the rainwater, put it in a clean bucket, send it to a lab. The bicarbonate's going to be like almost nothing, 50 part per million probably, roughly. So it's really, really good water. The problem is it hits the ground, runs into the pond, and what you actually send to the field has a bicarbonate level about 350 to 400. Now there's a question about where did that come from, and is it as damaging as the bicarbonates that get pumped out of groundwater? And how they measure those bicarbonates are a little bit in question. But yes, it's very high bicarbonate. It's a very high pH. The pH of most of our pond water is around 8, 8.5. You get some algae blooms, your pH will be over 9 or 10. There's not a lot of buffering in it. In other words, it doesn't take much to bring it down. But we're off the chart. Now, I have a chart in one of my water quality presentations looking at the pH of rainfall. pH of rainfall 20 years ago was 4.5 to 5. Every time it rained, it fixed this problem, right? I collected some rainwater about 2 months ago. The pH was 6.2, and it's continuing to go up. Okay, so the pH of rainfall is directly impacting this long-term impact of bicarbonates in the soil, and I think it's the reason it's starting to show up more and more. If we don't address it, I think we're losing yield because of it.
River water different from pond?
No, be the same. Yep. I mean, there may be a few exceptions here and there, depending on where it, what it ran off of and what it ran through. But by and large, we're a calcareous soil in northeast Kansas, and so it's picking up calcium as it goes, as it gets in the water. So, what is, I'll ask Jason this first. How much of our, so let's say on our farm here, our phosphorus application is dry banding 1152O in a strip till bar. That's how we do almost all of our phosphorus. Some guys would do dry spreading. How much of that actually gets to the plant? I know I've read the answer to this. I don't know if I know the answer. I've read what other people say, but I'm curious if you have a thought on that.
In the first year after application?
Yeah, first year.
Yeah, so I think the phosphorus use efficiency number sticks in my mind, Kurt's maybe around 20%. So of what you apply, 20% is available for the crop in that season for which it was intended. And then, phosphorus is subject to all the chemical reactions that we kind of highlighted for water, water and soil. So, it gets tied up with calcium, with magnesium, aluminum, depending on the soil pH. And with something like, calcium phosphate, I mean, that is rock phosphate. I mean, that's what Mosaic or ICL or any phosphorus producer mines from the soil is calcium phosphate. It's a rock. It's really, really hard, not very soluble. And then how do you produce phosphorus fertilizer? How do you produce triple superphosphate or MAP, these granular fertilizers that you apply to your field? You add acid to break down the calcium phosphate and make that phosphorus available to the plant. So that kind of brings us back to the use of acid forming fertilizers, is that we're trying to make that phosphorus available in the water if we're fertigating, but then for a soil application like the starter applications, we're acidifying the soil in that zone of application to make that phosphorus as available to the plant as well we can.
So a book I read this winter, some research out of Texas says that it's more like maybe 5 to 10% available. So 20% would be on the high end. So if, let's say you spend $100 on phosphorus, you're getting somewhere between $5 and $20 worth of it back. What about on a phosphorus that's applied through irrigation? Any ideas on what efficiency factor we would have on fertigated phosphorus? Properly applied.
I don't know, Kurt, but I think you're going to tell us.
So the same book that came out and said 5 to 10% on dry spread or strip till is saying 50 to 60% on properly fertigated. Mm-hmm. So is this product more expensive than 1152O? Yes, but what's our efficiency? Terry?
The other 80% of the phosphate, is it available and how fast or not at all?
Yeah, repeat the question. So is the other 80%, is it available at all? Where does it go? Can the plant ever get a hold of it?
Well, I think that kind of ties into the conversation about soil health, which is more of a long-term play and encouraging microbial activity, fungal activity, et cetera. But microbes play a huge role in nutrient cycling and making those nutrients available to the plant over time. But then the thing that I would add is, how do microbes make phosphorus more available in the soil? They secrete acids. So you've got kind of a two-pronged approach where you've got phosphorus in the soil from your fertilizer applications over time that could become available to the plant if you've got bacterial activity, microbial activity, or you can use a faster approach to supplement using acid through fertigation or an acid forming fertilizer banded to the soil.
And I would echo that. We've got some test data from this year over on a test plot by Morrill, where we applied the phosphorus levels in the soil test are super high. It's had long-term manure. This is on Kent's test plot. So lots of phosphorus in the soil. Tissue values are very low on phosphorus, not sufficient. All right, they're average for this area. I would say in general we struggle with phosphorus uptake. And we applied the infuric, so sulfuric acid with urea. We didn't apply any phosphorus. 2 weeks later, his phosphorus levels in the tissue were double. So we didn't apply any phosphorus. We simply released what was in the soil by putting acid in there. So can you get it available? Yes. And I think to the point of biology, right? Phosphorus solubilizing bacteria, what else can you do there to help make that available? So is it available, or would it be available eventually? Yes. But ultimately, when I look at our tissue samples, they're about half where they should be on our phosphorus levels. So it's one of the things we're going after as, like, we've got to fix this.
Yeah, the trendy thing in the plant nutrition industry right now is enhanced efficiency fertilizers, or some terminology like that. And I think sometimes, and oftentimes, those enhanced efficiency fertilizers have a very low use rate associated with them. For example, in the starter trials that I showed, the one rate of the ICL product supplied 2.7 pounds of phosphorus, and the higher rate was 5.4 pounds of phosphorus per acre. And conventional wisdom would say, that's not possible. You're not going to get a response from that because the crop needs more. And it's true, the crop does need more. We're not trying to supply all of that crop's phosphorus requirements with those low starter rates. But to Kurt's point, if the phosphorus use efficiency is only 5 to 10%, that means there's a huge opportunity and a lot of room for big gains with the right types of products, formulated correctly. Thinking about the effect of pH, those types of things. And so I believe that's how we can have those high levels of efficiency with low use rate products, whether they come from ICL or BW Fusion or any of the other leaders in this space. So.
Other questions?
Looking at the nutrient uptake curve, what are you guys seeing from the time you fertigate to seeing the tissues rise?
Yeah, I'm going to repeat the question for those online. So looking at nutrient uptake charts, what's the time from the time I apply something until I'm going to see it in the tissue? You want to take that first?
I can't speak to NutriDrip's experience with this, but going back a number of years now with the University of Illinois that Kurt mentioned at the beginning, company I was working with at the time, and I did some trials, fertigation trials, through the growing season, specifically targeting nutrients like potassium. And what I would say is that within just a few days after application, we could see that benefit in the crop. And with repeated fertigation through the growing season, the difference, particularly for potassium, between the grower standard approach and then the fertigated potassium approach was huge. Both of the treatments kind of followed the same pattern where you had high amounts of potassium in the plant early in the growing season, and then it tapers off as the plant gets bigger and bigger later in the growing season. But with fertigation and fertigated potassium, we were able to move that curve, shift that curve up higher so that we were able to maintain optimal potassium levels in the plant throughout, pretty much the entire growing season, or at least most of the growing season, compared to the grower standard practice, which, crashed, a lot sooner in the season.
And I guess I'll add to that. I would say it depends, and if you get too far behind early, it's hard to catch up. Sometimes applying things don't necessarily give you a positive response, but they keep you from dropping further. That's probably more of our experience is like, okay, we didn't see an increase, but it didn't fall off like it normally would have. And then a plant that's already super deficient in something or already out of balance, to bring that thing back into balance is really hard. It's more about starting that season off right and staying in those ideal bands. And that's where I think, for us, tissue sampling is, we make a few in-season decisions with it, but it's almost more about what are we going to change next year, right? How are we going to prevent those dips? How are we going to keep the levels higher? How do we start off right? There's a drastic difference based on management practices for what we see on tissue values.
Yeah. High yielding crops are a relay race. Start strong with the base soil fertility or the starter, the 2x2 applications, whatever the case may be, and then follow that through the growing season. According to a plan, and like Kurt said, you can make some modifications to that plan based on tissue testing. But I think it's more important to have a plan and to stick to it so that you don't get behind. And then based on what you learn from that season, you make adjustments based on the outcome and the tissue test to the next year's approach.
Yep. Other questions? All right. Yeah.
There was a question here
online.
Can cover crops directly assist with P availability, or are they helping the soil health equation and biological function, which allows for better P release?
I guess I'll go first on that. It can definitely help because all plants exudate acids, right? That's what a plant exudate is. It's a low pH exudate that starts that process quicker, keeps it going longer. And so definitely my opinion is yes, that can definitely help to have that happening in your soil for a longer period, especially in high pH soils. I think that's definitely something that we've seen. Is that going to help me on a pH where my subsoil is 5? Probably not as much. I'm more interested in soil structure. How can I change my soil structure and get my clays in better condition versus, so that's not necessarily my goal on our soils, but I think we've got a soil structure problem that I'm interested in fixing with cover crops maybe.
Yeah. So I got two thoughts. I mean, one, like Kurt said, the microbes in the plant, they're partners. They work hand in hand. The plant feeds the microbes, and in turn the microbes feed the plant. So the more that we can have an actively growing plant in that field, or the more months of the year that we can have a plant in that field, the happier those microbes are going to be, as opposed to purely having an annual crop of corn or soybeans and then fallow bare ground in between. There's a lot of start and stop for the microbial community, or at least that's what the theory would be. The other thought I have, Kurt, is with specific cover crops, and specifically I'm thinking about deep-rooted cover crops, tillage, radish, etc. They're recovering some of those nutrients that have been maybe lost over time to the subsoil and bringing them back up to where the cash crop, the corn, the soybeans, etc., are going to have more of their rooting, more of their active rooting zone when they're growing in that field.